Hello everyone, I'm back. I'm Gangada Venkatramana, and today I'm with the topic of design and analysis of convergent divergent nozzle using MATLAB and SolidWorks. Okay, um, this is actually my seminar topic in 2018. Okay, let's go to the abstract. Um, my basic concept is to develop one-dimensional equations and applying these one-dimensional equations to giving these one-dimensional equations to the MATLAB program and to develop a graphical user interface and using the outputs that are given by the graphical user interface and those one-dimensional equations. We are going to construct a three-dimensional nozzle and using the SolidWorks flow simulation, that nozzle is again numerically validated with computational fluid dynamic analysis. Okay, and these are the contents, and this is how the process will go on. And the first thing is we have to give the inputs to the MATLAB program and the MATLAB graphical user interface, and this interface will give us the nozzle diagram and the nozzle outputs or nozzle parameters, geometrical parameters, or either flow parameters as the boundary conditions will be given by this graphical user interface, and this will be continued, and these geometrical parameters and boundary conditions will apply to the a model that was generated in the SolidWorks CAD model. Geometrical parameters are used in SolidWorks CAD, and the boundary conditions that are as output given by the MATLAB are used in the flow simulation window, and then the report will be generated based upon these results. What are the results that came as output from the flow simulation should be equal to or should be approximately equal to the inputs that we have given to the MATLAB program. That means it is a reverse validation. The flow conditions as boundary conditions is output of MATLAB GUI. So the output of this CFD, whatever the nozzle output Mach number or nozzle output stagnation temperatures or different parameters, should be the equal to the inputs we have given. So that's how we are validating here. And the next slide is we are now going to the MATLAB programming and graphical user interface, and this is how these are the inputs we are going to give in graphical user interface. The Mach 2, that means what is the type of nozzle we want, and nozzle inlet diameter, and what are the ambient pressures and ambient temperatures. We must show that there is a condition, the inlet diameter and the outlet diameter for the nozzle, that is convergent divergent nozzle, is same here. I'm going to the second. So for this case, we Mach 2 is shown here as a design Mach number. Let's see in the next slides on what are the case we are dealing with. This is the processing program. Those are the inputs that I have given in previous slide that are taken at this location. That is, ambient pressure will be taken here, and ambient pressure will be converted to the number, and ambient temperatures, that is converted to number. And we are, since we are using air or ideal gas, it is a gamma equal 1.4, that is a constant, and the Mach number will be input that I have given in the input chamber will be taken here, and this will be processed in the next segment. Okay, and these are the outputs. These are some outputs that will be given by our MATLAB GUI. It will give the nozzle length. The nozzle length is actually defined by the angles. But since this is a linearly varying area ratio nozzle, the angles the convergent angle and divergent angles are given respectively in such a manner that they are less than 8, and convergent angle is greater than 10, or divergent angle is less than 8. In such a manner, this was designed. And the nozzle length for this case, we have given Mach 2. this is the nozzle length, and this is the density ratio, and this is the pressure ratio. What is the pressure ratio mean? Is the ratio of exit static temperature to inlet stagnation temperature. So this is the stagnation pressure we have to keep before the nozzle or in front of the convergent portion, and minimum inlet stagnation pressure to choke the nozzle. Um, Actually, these outputs is showing here are not actually belongs to the Mach 2. This is for the general purpose. Consider these outputs only. These two outputs are clearly saying that minimum inlet stagnation pressure to choke the nozzle means a certain amount of pressure is required to choke the nozzle, and the output is showing like m greater than 1. Purposefully it is showing that m greater than 1 because the condition to choke the nozzle is we must operate the operating pressure in such a way that the nozzle should be choked. So it was found that there is no Mach number or the maximum Mach number still under 1. So it is showing there is no Mach number, there is no presence of Mach number greater than 1. So to show these things, and whatever different conditions in the nozzle, to show these things, it is represented as m greater than 1, and we are showing different outputs of Mach number. And through that means whatever the ambient pressure we place it there, or whatever the Mach number we place it there, is for the different cases. Okay, and this is the throat diameter, this is the area ratio for the respective Mach number, and this is the temperature ratio, and this is the stagnation ratio. And this is how our nozzle as output and two-dimensional plot is the area ratio contour. We can see the throat area is approximately 0.1 as per we designed, and the length of the nozzle is totally normalized from 0 to 1. Here it is 0 and it is to 1. It is normalized, and these are the angles as said earlier: semi-divergent angle 10 degrees and sorry, respectively semi-divergent angle is 2.5 degrees and convergent angle 10 degrees. And this is the area ratio nozzle, straight area ratio nozzle varying linearly. And this is the total graphical user interface that was developed. And purposefully here we are showing that design Mach number is 1. This is because to generate the design Mach number 1 at the exit of the convergent divergent nozzle is actually not possible. So to generate Mach number 1, it is necessary to develop only convergent nozzle. So this graphical user interface is aware of this particular problem or this particular condition. That means if the design Mach number is 1, it can automatically generate the convergent nozzle. If the design Mach number is less than 1, it will generate the convergent divergent nozzle, or if the design Mach number is greater than 1, it will develop convergent divergent nozzle. Especially for the design Mach number 1, it is generating the convergent nozzle only, and the respective outputs are this. Okay, these are the respective outputs. And for the design Mach number 2, this is what we are going for the different types of Mach numbers from now. This is the design Mach number 2, and we can clearly see that what is the minimum inlet stagnation pressure to choke the nozzle. Okay, this is what minimum stagnation pressure. And if you see that this stagnation pressure, this is 790 and this is 311.141. So this is always less than the stagnation pressure. This is for the perfectly expansion. This stagnation pressure is for perfectly expanded nozzle. This stagnation pressure is actually to choke the nozzle. Okay, and this stagnation pressure and this pressure that is actually required to place a normal shock wave at the exit of the nozzle. Okay, these are the various things. And let's see for the different how the focus on this area. From now onwards, for up to few slides, this area will this plot will continuously change, and how the contour of the nozzle and how the plot of the nozzle will vary with the design Mach number. Let's see for the Mach number 3. You can see how it is varying. For this is for the Mach number 3, and now going for Mach number 4 and Mach 5, 6, 7, 8, 9, 10. Okay, for 10 Mach numbers, we have seen that how this profile is varying, and for all the sections the throat area is continuously um, reducing. This is the reason, I mean, this is actually the relation between area Mach number relation. This is due to the area Mach relation. So as Mach number is increasing, the throat area is continuously decreasing. We have to deal up to only Mach number 5 because that is the supersonic level, and hypersonic levels the equations may be different, and at the Mach number 17 the program fails to give a good results. Okay, and now we are going to SolidWorks modeling and flow simulation. This is the SolidWorks equation manager to develop the CAD model of the nozzle. To develop the CAD model of nozzle, we actually require the inlet dia, throat dia, thickness, semi-convergent angle, and semi-divergent angle. These are made as equation. These are given to the equation manager. So equations and the values that we can modify here to not disturb the model. And this is the model, and this is totally parameterized. This is a parameterized model, and the constant one is here is the thickness. Thickness is not a problem in the flow simulation because it's always given as a static wall in the flow simulation, so it is kept as constant. 3D model, and this is the generated 3D model for the convergent divergent nozzle. And here we can see that the above nozzle is designed for the isentropic flow equation producing for the Mach 3. The above nozzle is actually designed for the Mach 3. So the conditions, boundary conditions are all can be taken from MATLAB graphical user interface outputs, and that conditions will be given as the boundary conditions to the SolidWorks flow simulations. These are the outputs. We have given the ambient pressure or static pressure as 101,325 in previous slides. Our ambient pressure is always set to the atmosphere, and the total pressure or the stagnation pressure that should get in front of the convergent nozzle to make the flow is isentropic or perfectly expanded. To make the flow is perfectly expanded, this static pressure should be kept in front of, so this stagnation pressure should be kept in front of the convergent nozzle, and the flow is perfectly expanded for this case. And this is the mesh generations, and we have given manual mesh generation with the cell refinement. This is actually a plain representation of mesh. Coming to the flow simulation, this is how the flow during the, I mean, how the numericals are progressing during the iterations will be seen from this slide. At after 42 iterations, this is the contour and the flow. I mean, these are the numerical values. These numerical values are proceeding and converging during the iterations in this manner. We already know that the actual design Mach number for the nozzle is 3, and our output is approximately 3. This is the Mach number contour, and this is the exit perfectly expanded flow. So this is solver status is finished, and the exit Mach number is 2.92, that is approximately equal to 3. And this is the animation for the Mach 3 nozzle. This is how the flow. Okay, in the next slide you can see that the line animations of the flow or the streamlines. We can see these waves or the Mach waves to give the information for the backflow, and going to this is the conclusion. So we have seen the MATLAB program, MATLAB graphical user interface, and inputs we have given to the MATLAB program, and the boundary conditions and geometrical parameters is given by the graphical user interface. Those boundary conditions and geometrical parameters are applied to the flow simulation model and geometry of the nozzle, and again it gives out correct results or approximate results, that is Mach 3. We have given the Mach 3 as the input to the graphical user interface, and hence it generated the output as also Mach 3 nozzle from the flow simulation. These are the references. Thank you.